All right, today we are picking up with our second day of u-substitution and our final day of u-substitution. I apologize in advance. I'm a little sick right now, so pardon that, but we'll get started. Yesterday we talked about u-substitution and how if our integral is not one of the basic integrals that we've learned, that we have to figure out a way to rewrite it, and u-substitution helps us to do that. It's the reverse of the chain rule. So in this case, if we were taking the derivative of cosine of 4x, I hope it's obvious that we would need a chain rule since we have that 4x inside of the cosine. I know that the way that it's pictured originally, the 4x is not in parentheses, but I hope that you can imagine that that 4x is a part of the cosine, that it's inside of it. And so we would treat that as our inside function, and cosine is the outside function. So when we set up our u-substitution, we say that u is equal to 4x. The derivative of u du is equal to 4 dx. We need the 4x. We don't need this extra 4, however. So in order to get rid of the 4, remember we just divide it over to the other side. So that would be 1/4 du is equal to dx. If I'm looking at what I can replace, this 4x can be replaced by u. And then this dx can be replaced by 1/4 du. So when I rewrite this with u-substitution, I get 1/4 times the integral of cosine of u du. And remember, we can pull that 1/4 out front as a constant multiple because I would do it later anyway, so I might as well do it at the beginning. Excuse me. And now this is one of our basic integration rules. I have my little rules for differentiation and integration cheat sheet in front of me. Hopefully you guys printed that out as well. If not, I linked it on the calendar this past Monday. So go ahead and look at it and print it out if you haven't already done so. It's nice and helpful to have that with you, especially when you're doing the trig integrals, just because sometimes they can get a little confusing with the signs and everything like that. So while you're first learning how to do it, it's helpful to have this little cheat sheet in front of you to kind of go forwards and backwards. So the integral of cosine, if you look at your little cheat sheet, is sine, and it's a positive sign. So the integral of this is going to be 1/4 times positive sine of u plus c. And if I replace u with what it equals, that's 1/4 times sine of 4x plus c. And that's our final answer. And again, just like I said in the video from yesterday, while you're in the process of going through these integration problems, it's helpful once you get to the final answer. It's helpful to go back forward again and take the derivative to verify that it makes sense to you as to how we got that answer. So for example, if you take the derivative of this final answer, the derivative of sine is cosine. The derivative of the inside, which is 4x, would be 4, and then when you multiply that 4 times the 1/4, the constants disappear. So that's why there's no constant in the original problem. So hopefully that makes sense to you. If I have a little link down here in the corner, by the way, it says don't forget to use your derivatives and integrals cheat sheet. If you want to click on that, it'll take you to a link of that cheat sheet that I put on the calendar. So you can find it in either place. You can either click on it from here, or you can go back to the calendar and click on it. All right, let's keep going. 14. Slide 14, the parentheses are a little bit more apparent in this case. So u is equal to 1 minus 3x, the inside of the parentheses. The derivative of that du is equal to negative 3 dx. Now, I actually do want that 3 in there because I have that extra 3 in front of the sign, but I don't want the negative. So I'm going to get rid of the negative by dividing it to the other side. So that's negative du is equal to positive 3 dx. And if I start to highlight some things I can substitute, 1 minus 3x is going to be substituted for u. And 3 dx will be substituted for negative du. So there are no more x's left in my original problem, and that's very, very important. I don't want any x's or dx's or anything like that left, because if I'm going to change over to being in terms of u, everything needs to be in terms of u, not just certain things. So let's go forward from here. If I make this substitution, remember that the negative from the du, let me see if I can rotate this. There we go. The negative from the du is a constant multiple. I'm going to pull that out front. So we have negative integral 3 dx is going to be replaced with du, so I'll write that at the end, and we already took care of that negative. So inside we just have sine of, and then 1 minus 3x is getting substituted or replaced by u. All right, so we have negative sine of u du. I have my little cheat sheet out. The integral of sine is negative cosine. So this is a negative cosine of u plus c. Notice that I didn't include the plus c in the parentheses with the negative, because if I distribute a negative to a constant, it's still a constant, and it really doesn't matter if it's plus c or minus c. When we go to figure out what c is, it will become apparent what it will be depending on what it is. So I don't really worry too much about that negative being distributed or constants being distributed or anything like that to the constant value. So the negative makes a positive cosine of u plus c, and if I substitute u back in for what it equals, this is cosine of 1 minus 3x plus c. And that's our final answer. And again, go ahead and take that derivative just to verify that it makes sense to you as to how we got that. All right, for number 15. Here's where it starts getting a little bit more tricky in the sense of you having to do a little bit more thought process to find out what the inside and outside functions are. Because there's no parentheses necessarily that are apparent in the problem. We're going to rewrite this in a way that it makes a little bit more sense as to how the parentheses come about. But the main thing we're looking for, and I mentioned this in the last video, the main thing that you're looking for is this whole idea that the inside function is chosen so that when you take its derivative, you're able to eliminate other pieces of the function. So when we were doing it with polynomials yesterday, we talked about how like the inside function would be a quadratic, so that if you took its derivative, it would be a linear function. So like you wouldn't choose the inside function to be the one with the smaller degree. The same thing kind of applies here in the sense that with sine cubed of x and cosine of x, when I choose what I want my inside function to be, I need to make sure that when I take its derivative, I'm able to replace that piece of the equation with that as well. So it can take some practice and some getting used to make sure that you're on the right track in terms of what you want your inside and outside, or your inside function to be. But keep practicing with it. It becomes easier the further you go. So I just want to rewrite this really quick. I hope that we're all clear that sine cubed of x written that way is the same thing as, oh my gosh, there we go, is the same thing as sine of x cubed times cosine of x dx. And I want to make sure you understand it written that way, because if we write it this way, then it kind of becomes apparent as to what the inside function is, because now we have this set of parentheses, and that kind of can sometimes indicate what our inside function should be. So in this case, I believe, and I hope it's apparent, that our inside function is going to end up being sine of x. So our u substitution is going to be with sine of x. And before we even go any further, I just want you to kind of make this mental note that if I make u equal to sine of x, then when I replace sine of x here with a u, that this will go away, so that's good. Notice that I'm still going to have this cosine of x left over, however. So that would be a bad thing to leave in our equation. We need to figure out a way to get rid of that, because we're not allowed to have x's and u's mixed up in the same integral. So keep in mind that when we take the derivative of sine of x, it equals cosine of x. And so that's going to help us make that replacement. And that should always happen with our u substitution problems, where whatever we choose for u, it works out to replace everything in the equation, so we have no more x's left. So if I say du is equal to cosine of x dx, then I can show you by highlighting what is going to be eliminated from this equation. So notice that my u is going to replace sine of x, and my du is going to replace cosine of x dx. And now we have no more x's left in our equation. Everything is highlighted over here to the point where I know all of my x's will go away, and I will only be left with u's in the problem. So this can be rewritten as the integral of u cubed, because sine of x was replaced with u, and then cosine x dx is being replaced with du. And now this is a much, much easier integral to solve. The integral of u is u to the 4th over 4. plus c. And if I replace u with what it equals, that would be sine of x to the 4th power over 4 plus c. Number 16. Our u in this case, we're looking for an inside function. And again, there's no parentheses necessarily, but if you notice how I can do this, this is tangent of 10x and secant of 10x. And if you look at your rules for differentiation and integration cheat sheet, you'll notice that one of the rules is the integral of secant tangent, or in this case, tangent secant. So our inside function is going to be 10x, so u equals 10x. The derivative of that du is 10 dx. I don't want that 10, so I'll divide it over to the other side. 1/10 du equals dx. And then I'll go ahead and proceed to highlight everything that's going to be substituted. So each of my 10x's will be substituted with a u, and my dx will be substituted with a 1/10 du. So if I do this substitution, I get 1/10 times the integral of tangent of u, secant of u, du. And my cheat sheet says that the integral of secant tangent is secant. So this is 1/10 secant of u plus c. Last but not least, I'll replace u with what it equals. So this is 1/10 secant of 10x plus c. Final answer. This one can sometimes trick people because they have a hard time figuring out what u should be, but I want you to recognize the patterns that you see here because this is a very common problem on the AP test actually, in the sense of making your inside function equal to what the trigonometric function is being taken of. So try to keep that in your repertoire of tactics to use in problems like these, is looking for the inside function as what is inside of the trig functions. Because some people get confused with the whole like two different trig functions in there and they have a hard time manipulating it to see it correctly. So do the best you can to see it in that way. And then again, to make sure that you believe this, go ahead and try to take its derivative and verify that it equals what we have up here. All right, number 17. Now, as you're looking at number 17 and trying to figure out what to make your inside function and what to make your outside function, there's a couple different ways to rewrite this. And so I want to kind of show you the different ways and show you how you might go through a process of trying to figure out what u is and then figure out the wrong u. And I want to kind of show you how you would know it's the wrong u from the very beginning before you do any work. So for example, the first time I saw this problem, I looked at it and I was like, oh, we can rewrite this as tangent x secant x quantity squared dx. And then I said, okay, if I rewrite it like that, tangent secant could be my u, but then I was thinking, oh, the derivative of tangent secant is kind of a big, long thing. You have to use product rule, and we get into all these crazy derivatives. And I don't see anything else outside of this that needs to be replaced. So that would be a problem to bring in these extra x's that don't necessarily need to be replaced. So if you saw that as well, that's good that you saw that, but I hope that it becomes apparent pretty quickly that the derivative of this is nowhere else in my problem. And so that's kind of a null point, that that's definitely not going to be our u. So let me come back to the drawing board and see if we can figure out a different way to rewrite this. We have tangent of x quantity squared and secant of x quantity squared dx. And so here's another way to rewrite it. And I think this is a better way, but the thing with this is that we still have two inside functions, technically. We have an inside of tangent being inside the parentheses, and we have an inside of secant being inside the parentheses, which could be confusing on which one to choose. So again, let's try to be logical with our derivative rules. So I'll kind of show you two different ways. Let's say that you decided to make u equal to tangent in one instance. Let's say we decided to make u equal to secant in the other instance. Well, the derivative of tangent is secant squared. secant squared x dx. And the derivative of secant is equal to secant tangent. Secant x tangent x dx. So looking at these two options for what u could be and what du could be, I want to be able to replace all of my x's without bringing in extra x's or anything like that. If I go with the first scenario, we have tangent of x. That would replace this. This would be my u, and then u squared. And notice that its derivative, secant squared of x, replaces this piece. So secant squared of x dx. So I'm kind of liking this one, leaning towards this way. But let's just explore this other option if we had chosen to make u equal to secant of x. If I did that, secant of x would replace this piece of it, and this would be u to the power of 2. Down here, however, I still have two tangents that I need to replace, and this derivative would help me replace one of the tangents, but then it would bring in this extra secant, and it wouldn't replace the other tangent. So I don't think this is the best bet because, like I said, it's not a perfect match for the problem we have written out here. So sometimes it is a matter, when it's choosing your u value, it is a matter of going through all the possibilities of what could I make u equal to? Does it make sense to make it equal to that with the derivative I need? So you can see we've done it 3 different ways now. The first way definitely didn't work. Of these 2 ways, I think we found one that probably will work and one that was close but didn't quite work out, and I don't want to have to fudge anything around to make it work. So let's go this way that lends itself much more helpfully to u substitution. So I'll erase this. And now if I highlight what I'm going to be replacing, tangent of x is going to be replaced with u. And secant squared of x dx is going to replace with du. So if I make that u substitution, I get the integral of u squared du. The integral of u squared is u to the 3rd power over 3 plus c. If I replace u with what it equals, that's tangent cubed over 3 plus c. Final answer. And again, take its derivative just to verify that you actually do believe it and that it makes sense to you. All right, 18 and 19. Okay, with 18, I think it's pretty apparent what the inside function is because it's what's inside of grouping symbols like parentheses or what's inside of a radical. So in this case, we do have a radical. And that helps us to kind of decide what, oops, too far. There we go. That helps us to kind of decide what we want u to be equal to. So we'll say u is equal to cosine of x. And again, the reason I wouldn't have chosen sine of x, even though both of these are each other's derivatives, the reason I wouldn't have chosen sine of x is because the derivative of sine of x is just the cosine, but I don't want to have to keep my du underneath the radical, so I wouldn't ever put that underneath there. So we choose u equal to be cosine. Du is equal to negative sine of x dx. I don't need that negative, so I'll move it over to the other side. Negative du equals sine of x dx. And if I make some substitutions, cosine is replaced with u. Sine of x dx is replaced with negative du. If I rewrite my integral, I have a negative integral of the square root of u du. There we go. If I rewrite this, I have negative integral of u to the 1/2 du. That's negative u to the 3/2 over 3, and then times 2 for that 3/2, plus c. And if I do my final substitutions, this is negative 2/3 times cosine of x to the 3/2 plus c. And again, you could write it like this, or you could change it back to being in radical form if you wanted to. But either of those would work. All right, number 19. I would encourage you to pause the video possibly, see if you can get started on this, and come back and check your answer at the very end. Or if you get stuck, push play and see if you made a mistake or if you're on the right track and you just need a little bit of extra help along the way. All right, so for number 19, again, for our u, we always like to choose what we have either inside of parentheses or radicals or grouping symbols or on the bottom of fractions or whatever the case may be. So in this case, we have something that's on the bottom of a fraction, which is the square root of 1 minus sine of x. I don't necessarily want to make u equal to that entire thing because that square root is going to give me an interesting derivative, and I don't want to have to go through that whole process if I don't need to. So instead, I'm going to make u equal to what's inside of the square root, which is 1 minus sine of x. The derivative of that du is equal to negative cosine of x dx. I don't think I need that negative, so I'll move it over to the other side. Negative du is equal to cosine of x dx. If I do my highlighting to get rid of some stuff and change it into u's, 1 minus sine of x will be replaced with u. Cosine of x dx will be replaced with negative du. So this is negative integral of... Now notice that the square root is on the bottom of the fraction, and it needs to stay on the bottom of the fraction. This is a mistake that's commonly made with students, is that when they do all these replacements, especially in fractional form, they get confused on what's on the top and what's on the bottom, and they forget about that. So please make sure that you understand cosine of x dx is on the top of the fraction, so this negative du remains essentially on the top. I'm going to put a 1 on the top, because I'll put my du over here at the end, but it means the same thing. And then on the bottom of the fraction, I'm going to keep the square root of u. So this is negative. I'm going to rewrite this as u to the negative 1/2 du. If I integrate that, I get negative u to the positive 1/2 over 1 times 2 plus c. So this is negative 2 times the square root of 1 minus sine of x plus c. Final answer. And last but not least, this problem, again, I mentioned earlier about how this is sometimes a very common problem for us. So this is from a previously released AP test. If you want to go ahead and pause the video and try this one on your own. And so if you're coming back with us, the reason I said it's a common problem is because they like to make the u equal to what's inside of these trig functions. So if I set my u equal to 2x, then du would be equal to 2 dx. I don't need that extra 2 anywhere. Both of these 2x's are going to be replaced with u, and I don't need an extra 2. So I'm going to move it over to the other side by dividing it. 1/2 du equals dx. If I start to highlight some things that are going to be replaced, my 2x's will be replaced with u, and my dx will be replaced with a 1/2 du. If I rewrite that, I get the integral, 1/2 times the integral of sine of u plus cosine of u du. And then these aren't being multiplied, so we don't need to worry about any special rules in terms of being multiplied. These are just being added, so when I take their integrals, I'll take them individually. The integral of sine of u, and I'm using my little rules for differentiation and integration cheat sheet. The integral of sine is negative cosine. So this is 1/2 times negative cosine of u plus the integral of cosine is positive sine of u and then plus c. If I distribute that the positive 1/2, I get negative 1/2 cosine of u plus 1/2 times sine of u. Oops, you can't see this probably. It's underneath that little symbol, but it says negative 1/2 cosine of u. All I did was distribute this 1/2. Negative 1/2 cosine of u plus 1/2 sine of u plus c. And last but not least, if I make my substitution with those u's, I get negative 1/2 cosine of 2x plus 1/2 sine of 2x plus c, which is answer choice B. Notice, by the way, on the AP test how similar all of the answer choices are. So the general format makes sense that it's cosine of 2x and then sine of 2x. The part that comes into question and the part that they're really testing in this question is whether or not you know how, when you take the derivative of 2x and you get 2, that when you move it over to the other side, it equals that 1/2, and you pull it out as a 1/2. So answer choices C, D, and E are there for students who forget to do that and just see the 2 and leave it as a 2 in the problem. So that would be one way to get confused, is by accidentally choosing one of those. Once you figure out that it's a 1/2, however, it's between a and b. And really the only difference between these is whether or not you realize that the integral of sine is a negative cosine rather than a positive cosine. So we don't have our little cheat sheet on the AP test. It's important for you to understand all those rules on your own without needing the cheat sheet. Obviously, for right now, while we're still at the beginning, please use it. But when we get closer to testing times, it's important to know all of those rules by memory, so you don't need to worry about using your cheat sheet all the time. All right, that's the end of u-substitution.